successfully.
Hello guys, hello everybody. As promised, I will be able to solve one gas stoichiometric problem. Okay, this came from Chemical Engineering for Examination 1998. As what I told you a while ago, we attempt to solve this yesterday, but I doubt there's a missing quantity or property of a gas, which is the volume. Okay, then I stopped and looked for another problem. Okay, but this this time, guys, hello everybody, welcome to my live streaming. But this time, I'm gonna solve this problem. Okay, gas stoichiometric problem. Sorry for that. Applying the formula of ideal gas equation. But let's see if it is really an ideal gas. Okay, problem solving. Actually, this is gas stoichiometry problem solving. Okay, I'll put it again. So I'll put already the volume because I forgot to put in the problem. Okay, this is the problem. Okay, I want you to picture out the problem. Okay, I want you to picture out the problem also. Okay, guys, very right. I want to do the problem. Solid magnesium nitride reacts with oxygen liquid water to produce 4.7 liters of ammonia gas, 6 atmosphere. How many grams of magnesium nitride was consumed in the reaction? Okay. Chemical Engineering Examination, November 1998. Okay. A, 14.4 grams. B, 15.17 grams. C, 12.18 grams. D, 11.14 grams. E, none of the above. Okay, this type of question class is average. Average, not difficult, not easy, but somewhere in the average atmosphere of solving this problem. Okay, the first thing to do is to analyze the problem. So we have a chemical reaction here between the solid and the water. Okay, like that. And I will draw now the chemical reaction. Okay, release. Okay, solid magnesium nitride. So guys, what is the symbol of nitride? Based in our chemistry before in high school, we have the fluoride, okay, the sulfide, the chloride, chloride -1, sulfide -2, okay, and then for the nitride that is -3, okay. So magnesium nitride, magnesium nitride. So it's gonna be here like this, and this is solid. Okay, this one magnesium nitride, magnesium nitride. Okay, solid. So plus liquid water, liquid water to produce ammonia, ammonia gas plus is gonna be magnesium, okay, magnesium hydroxide, okay, magnesium hydroxide. Okay, so OH2. This is gonna be solid. Okay? This is the reaction. Magnesium nitride gas plus liquid water is equal to ammonia gas plus magnesium hydroxide gas. Like that. Okay, this is the chemical reaction. The first step is you have to balance the chemical reaction. Magnesium 3 in the reactant, so we need to put magnesium 3 also in the product. Okay. We need to balance the number of atoms in each element and compound involved in the product and in the reactant to obey the law of conservation of mass. But the total number of atoms in the reactant must always equal to the total number of atoms to the product, so that we will attain the equilibrium stage between the rate of forward reaction and the rate of backward. 3 for the product, we have to do 3 also on the reactant. And now, nitrogen to the reactant and 2 in the product. The first thing to balance is the solid, followed by the liquid, and then the last will be the gases. Okay. Normally, the oxygen will be the last. Okay. So we balance the nitrogen. Look at the equation, chemical equation. Okay. Like that. Okay. Now hydrogen. Hydrogen in the left, we have 6 hydrogen. 6 plus 6 is 12. Okay. In the reactant, we have only 2. So 12 divided by 2 is equals to 6. To compensate the equality of the number of atoms in the reactant side and in the product side. So 12 divided by 2, okay, if there's 2, okay, in the H2 subscript, then is 6. Put the 6 beside the water liquid, beside or as a coefficient of the water molecule. 6. Okay. And now we need to have a final balancing equation moment, one by one. Okay. Magnesium 3 also in the product, nitrogen 2 in the reactant, and also nitrogen 2 in the product. 12 hydrogen in the reactant, and then we have also 12, 6 plus 6 in the product. Okay, let's try oxygen as the last to be balanced. So that is 6 atoms in the reactant and 6 atoms in the product. Okay, so these are completely balanced. We use this equation as our stoichiometric relationship so that we can compute the grams of magnesium nitride was consumed in the reaction. Okay, now write the given. Okay, given. Okay, the ammonia is the product. So the ammonia will be collected at, that is 4.7 liters. The volume of ammonia is equals to 4.7 liters, like this. Okay. Volume of ammonia, 4.7 liters. Okay. Now we have the temperature. The temperature is 300 Kelvin. Okay. And the pressure is 1.6 atmosphere. Okay. Guys, these are the parameters for operating condition. Temperature 300 Kelvin and pressure 1.6 atmosphere. Okay. Now, we need to identify if the amount of a non-ideal gas or a real gas. How can we identify that one? So we need to establish the theory and concept of kinetic molecular theory, the KMT, in physical chemistry or in chemistry. Okay, so if we said ideal gas, what are the requirements of pressure and temperature? Anybody like that? So this is the memorization comes in for the theory. Okay, because if you just keep on solving and solving, we don't know the theory and we will be lost because there are two types of gases, ideal gas and the non-ideal gas or the real gas. And we need to qualify the type of gas this ammonia will have after the chemical reaction of adding magnesium nitride and water liquid to produce ammonia gas and magnesium hydroxide. Now, in the theory of kinetic molecular gases, okay, or kinetic molecular theory, okay, if there is a high temperature and lower pressure, we assume that the gas product is ideal gas, not non-ideal gas. Or else we will be using the formula of non-ideal gas or real gas, obeying the van der Waals equation, real gases. So we need to consider first the ideal gas, and we have a formula P times V is equals to nRT. Okay, we will be using that formula. Okay, so formula to be used: ideal gas PV is equals to nRT. We're just assuming first if it is correct, basing on the theory, because it has a high temperature and a low pressure. That is the requirement of the ideal gas. Okay, PV is equals to nRT. We use this equation, okay, like this. PV is equals to nRT. P pressure, V volume, N is the number of moles, R is the universal gas constant, capital T is temperature in terms of Kelvin. Okay, like that. So here we have the temperature, with the pressure, we have the volume, then ammonia. But number of moles of ammonia is not the one we are requiring for. We need to find out the mass of magnesium nitride. So this is the time we need to have a calculation in our chemical reactions involving the number of moles and the PV in RT as we saw here. Okay, solve for N. Okay, like that. Guys, remember this: if you attack the problem solving regarding this type of problems, you usually think that the number of moles are always, dependent with this volume thing. Okay, if we have the number of moles, automatically we can have the volume. If we have the volume, we can have the number of moles. Okay, the number of moles in the chemical reaction is the actual number of moles needed to complete the chemical reaction. Okay, but the number of moles we solve in PV in RT is the ideal number of moles theoretically, not the actual. We correlate the theoretical number of moles from PV in RT equation to the actual number of moles in the chemical reaction. Okay, especially if we put this scenario in the chemical laboratory analysis, or in the laboratory, inside the laboratory. We need magnesium nitride, we mix that with water, and it produces ammonia gas plus magnesium hydroxide. And then the magnesium hydroxide will precipitate and form solid. And then this ammonia will vaporize, okay, but it will be collected here in this problem, okay? And then it could be a flask or any type of container that we form of collection, recovery, or collecting method. Okay, something like that. Okay, any kind of method you want to collect the ammonia gas, because that's ammonia is your answer here for your number of moles. Okay, so for N, number of moles is equals to pressure times volume is equal equals to R times T. And we have another data on the left. Here, then we can substitute the pressure and temperature like this. Our problem now is the universal gas constant. Okay, universal gas constant. R, capital R. So I memorized only two values of universal gas constant, capital R. The first is in terms of liter atmosphere, 0.08206 liter atmosphere per mole Kelvin, and the other one also 8.3146 joules per mole Kelvin. But in this problem, the data presented a volume in terms of liter and the pressure also presented in terms of atmosphere. Automatically, I will be using the universal gas constant that is 0.0806 liter atmosphere mole Kelvin, not the other one. Okay, because you have to check the compatibility issue that the unit will be agreeing with each other so that you can cancel somewhere along the way. Ganon. Okay? But then, there are a lot of universal gas constant. This is only good for this problem. Maybe other problems are presenting other units there, and then you have another capital R you'll be able to use in this ideal gas law equation. Okay? It's very clear. And then if you cannot memorize those other values of universal gas constant R, then just memorize that a standard temperature and pressure, a standard temperature at 0 degrees Celsius, 32 degrees Fahrenheit, and 273.15 Kelvin, and then 1 atmosphere pressure. Noted always that an ideal gas will occupy 22.414 liters. 1 mole of an ideal gas will occupy 22.414 liters of gas, something like that. Then use that volume to compute for your R, and then use the 1 mole in the end, small letter n, and then use the temperature, which is standard. Okay, I mentioned, which is the 273.15 Kelvin, not the 0, because the 0 it turns to be 0. Okay, so no more value anymore. Use the 273.15 because capital T in the equation PV in R stands for Kelvin unless otherwise specified. Okay, it's very clear. And then upon substituting in the ideal gas law, we can obtain the value of universal gas constant according to the problems presented, what kinds of units they are trying to present there during the actual examination. But for me, I memorized only 2. But when I was in college, I memorized a lot for that. So that it will never consume time for me when I solve this particular problem in ideal gas law, something like that. But it's up to you if you will memorize or not. But take note, it will consume time for you during the actual examination if you'll derive first the value of R. Okay? Because the examination is time limited and time pressured. So you should memorize supposedly something like that. Okay? And then memorize the values of volume occupied at STP. Capital S, capital T, capital P, standard temperature and pressure. Okay? It's gonna be like that. Okay, substituting values now. We are ready now to solve the value of N so that we can solve for the grams of magnesium nitride needed in the reaction. Okay, ganon. Okay. So substitute. Okay. Pressure is 1.6 atmosphere. Okay. Volume 4.7 liters. Okay. And then universal gas constant is 0.08206 liter atmosphere. Okay. Mole Kelvin times 300 Kelvin. Okay. Guys, if the unit of temperature is not Kelvin, you have to convert really every time with Kelvin. For example, if it is Celsius, convert to Kelvin. If it is degrees Fahrenheit, convert to Kelvin. Okay, because this is not change in temperature. Okay, not the same in the Q is equals to MC Cp delta T in the thermodynamics, because there's a delta change. Delta change meaning any kind of temperature you want to substitute. But this within RT always the standard Kelvin to be used. Okay, no other, something like that. Okay, so this one. Okay, like this, like this. So let's do the basic math for number of moles. Okay, 300. I have a calculator here. Okay, shout out Bell Buka Barikwato. Thanks for watching. Science moment. Okay, 300. Okay, oh my gosh. 300 times 0.0206 equals to 24.618. Okay, 24.618, and then 1.6 times 4.7. So our number of moles will be equal to 7.52 divided by 24.618 is equal to 130. Number of moles is equal to 130. 546. Okay, this one. Okay, guys. So we have the number of moles already. Okay, we get already the number of moles. Okay, you can see right? Okay, 3 something something. Okay, and we will use this. Now we will use this in this equation here. Huh? Here. Okay. Okay. Now we have the number of moles of ammonia is 0.30546. Already obtained that one. Let's continue our solution. Okay. 0.3546 moles of ammonia. This 0.3546 moles of ammonia, this one, this will be our basis to compute for the number of grams of magnesium nitride. So we can now refer the chemical reaction here. Okay, 13546 moles of ammonia. How many moles of ammonia in the chemical reaction? Wait, how many moles of ammonia in the chemical reaction? We have 2 moles of ammonia. Okay, 2 moles of ammonia. We are not referring to the chemical reaction. Okay. So if there are 2 moles of ammonia, then how much moles of magnesium nitride will react in this chemical reaction? How many moles of magnesium nitride will compensate and react to this ammonia? Okay, so the chemical reaction is very clear that we have, only 1 mole of magnesium nitride, because we're asking for magnesium nitride. Okay, determine the volume, okay, like magnesium nitride in the problem, sorry. Okay, how many grams of magnesium nitride was consumed? Okay, so magnesium nitride is 1 mole. 1 mole of magnesium nitride. Now, to solve for the mass of magnesium nitride, we need to compute for the molar mass. Okay, molar mass in relation to compute with the regular mass. Okay, something like that. So, we need to calculate the molecular weight or the molar mass of magnesium nitride. Now we should know what is the molecular weight of magnesium nitride, in which I don't know. Okay, so we need to 3 times the atomic weight of magnesium plus 2 times the atomic weight or atomic mass of nitrogen. The total will be the molar mass or the molecular weight. We need to use that here so that we can compute for the mass. Okay, diba? Molar mass formula is equal to the mass regular of any element and compound over the number of moles. So bingo, we can solve the grams of magnesium nitride. Okay, now 1 mole of magnesium nitride. Okay, magnesium nitride. What is the molecular weight? I think this is 190 point something. Yesterday I memorized. I think so. This will be correct. Approximately something like that. 1.90 let's say 0.49. Let's try that one also. Anyway, we can check. There are choices in the question. Choices A, B, C, D, and E. So let's just try 190.49, something like that. Okay, let's adjust the answer. The more closer, that will be the answer. Because I cannot use the Google to search for the molecular weight, and I don't have periodic table in my hand now. Okay, like that. Or it could be 190 I think so. It's gonna be basta 190.90 lang. Okay. Okay, anyway, the more closer is our answer, remember. Okay, because only point, decimal point. Okay, so cancel, cancel. So what remain here is the number of grams of magnesium nitride. Okay, you can check by yourself also the molecular weight and the molar mass of magnesium nitride. Okay, so let's do the math. Okay, 30, oh my gosh, 546 times 190.90. Okay, I know the nitrogen really, guys, 14. The atomic mass and atomic weight of nitrogen is 14. So 14 times 2, but I don't know the atomic mass and atomic weight of magnesium. Okay, that's it. That's the logic there. So 190.90 times 130, 546 equals 2 divided by 2. So we have 29.16 grams of 29.16 grams of magnesium nitride. Let's see if this value, mass of magnesium nitride, is in the choices. Okay, 29.16 grams of magnesium nitride needed. 29.16 of magnesium nitride needed. Okay, 29.16. Choices here. Okay, 14.4, 15.17, 12.18, and 11.4, and none of the above. It looks like none of the above because there's no 20 plus there. Okay, and if that is the case, you have to review your solution. It's very far. Okay, like that. And then after, you need to choose which is the best answer. Okay, that's gonna be the technique. Two times review only. Next review. Okay. 1.6. Fit in again the value. So 1.6. Okay. 1.6, that's 4.7. 4.7. Okay. 0.0826. Okay. Review. So 1.6 times 0.08206. Okay. So 0.08206 times 300. 24.16. Okay, let's review for the second time because our answer is a little bit far. Anyway, there's a choices E, none of the above, but let's not wait for that. 24.618. Okay, when 1.6 times 4.7 is equals to divided by 24.618. Oh my gosh. 0.30.5456 So most of this is for ammonia, right? Ammonia gas. Okay. Ammonia gas. So ammonia. So 0.30 is moles of ammonia, 2 moles of ammonia in the reaction here. And then how many moles of magnesium nitride is 1. Okay, then 1 mole of magnesium nitride, then ganon, 190.90. That's correct. Maybe we are wrong on the molecular weight because I don't memorize. I will check that later. Because I trust only the, my memory. Maybe my memory failed. Okay, times 0.30 546 is equals to divided by 2. It's really 29.16. But let's check the molecular weight of magnesium. Atomic mass of magnesium. Okay, wait for a while. I don't have the periodic table. I have to go and search for the atomic mass of magnesium. I know already the nitrogen. Wait for a while. Oh my gosh. Oh. Magnesium. Anybody? What is the atomic mass or atomic weight of magnesium? Anybody? Anybody can answer to me? Atomic mass. Because my phone is off, I will search in the Google. My goodness. Really? Okay. Let's check atomic mass for magnesium. I don't know. Okay. It's better to allow magnesium to memorize, right? I don't memorize. Okay. Nakapaloka. Wait for a while, Okay. Nakakaloka. Guys, I find the molecular weight of magnesium. Okay. Or molar mass of what is one? Magnesium nitride. Magnesium nitride. Okay, 100.94. Oh, see? 100.94. Guys, it's on the molar mass. I was wrong. Actually, that is 100.94. I used 190, so it's a very big difference. Okay, because my memory failed. Okay, so 100.49. Okay. Because it's not in the choices. Okay. But if there are in the choices, then I can solve. I memorize the raw molecular weight. Okay. So 100.49 times 0.3546 is equals to divided by 2 is equals to 15.34 grams. 15.34 grams of magnesium nitride. Class, you don't have to worry because you can bring your handbook, okay, your Paris chemical engineering handbook, but you can never bring other books except for the Paris chemical engineering handbook. It's in the first page of the handbook, the declaration of the periodic table. Okay, so it's very easy to locate, even though you will not memorize. Okay, like that. Still, you can answer it very well. Okay, in here I don't have. Okay, and then I have still to Google it, something like that, so that I could have. Because again, magnesium is not really common. Okay, the common only oxygen, nitrogen, carbon, hydrogen. So those are common, right? Sodium. Okay, but this magnesium I cannot remember it already. Really? Okay. So only few I can memorize for this atomic mathematics. Okay, but it's in the handbook siya, so it's easy to locate. Okay, our answer is 15.34 grams, and our choices here. Let's check again our choices here. A, 14.4 grams of magnesium nitride. B, 15.17. Oh my gosh, grams of magnesium nitride. C, 12.18 grams. 11.14 grams. E, none of the above. So 15.34 grams is closer to 15.17. So letter D is our answer for this. Okay. Okay. 15.17 grams. And let's check here. Okay. There is an answer here. Okay. Yes, letter B is the answer. Okay. So if I memorize the solution, then I can solve it perfectly, right? Meaning to say, I really solve this on the spot. Okay. I don't want also to prepare and then present the solution because it's not a challenge for me. No challenge at all. Okay. Letter B is the answer. 15.17 grams or 15.32 is just basically the same. That's only point something. Okay. So this is the mass of magnesium nitride was consumed in the reaction. Okay, like that. So it is really correct for this assumption. Yes, because the temperature is high, above 100 degrees Celsius, and then the pressure also is low. That is for ideal gas. What if it is the reverse, then this will no longer be applied if non-ideal gas or real gas. Now, after this problem class, okay, we need to conclude that in the ideal gas law obeys kinetic molecular theory. Okay, kinetic molecular theory. So in here, the compressibility factor is our identification or other identification apart from the temperature and pressure relationship requirements. Okay, if our compressibility factor Z is equal to 1, okay, this will be an ideal gas. Okay, but if this is not equal to 1, could either be less than 1 or above 1, then this is a non-ideal gas or real gas. Now, at our present situation nowadays, it is very difficult to obtain a compressibility factor of a gas which is equal to 1. Okay, from the name itself, ideal, there's no such ideal now exists in the planet Earth. Ideal means perfect. Okay, just the same way you will look for your ideal woman, you will look for your ideal man, meaning all the positive qualities you want from them, you will be able to get from them. But this type of gases ideal is not already existing in our planet Earth or in the atmosphere. Our gases nowadays are non-ideal gases and real gases. For the purpose only of understanding for the behavior of the gas. That's why our old scientists do that as our basis to understand and to interpret the behavior of the gases around us in our atmosphere. Okay? So, in real sense of the world, we need to use the van der Waals equation at this point in time. Okay? 2021. For example, if I will go out and I will compute the behavior of the air, I will use the van der Waals equation already. I will no longer use the ideal gas. You understand the point? So because it's not practical to use that one, because this ideal gas doesn't account also the intermolecular forces of the molecules. You know that? But nowadays, there are a lot of intermolecular forces involved because there are a lot of gases, exposures, and release from various chemical processes and industries. Then, of course, it will contaminate and react to the nitrogen gas and the oxygen gas in the air. So it's no longer perfect at all. The air is mixed with other gases, nitrous oxide, like this, magnesium oxide, okay, dinitrogen oxide, okay, H2S, and a lot of gases. Okay, what will happen? So it's no longer perfect. Okay, but the oxygen will normally adjust, not the nitrogen. Because as I told you, air is equal to nitrogen gas, 79%, plus 21% of oxygen. This is a perfect gas. So this gas or air, technically the same, obeys ideal gas law. And then there are a lot of gases now reacting, the greenhouse gases, the carbon dioxide, the carbon monoxide. So it will never behave now as an ideal gas. So the oxygen will be lesser, not 21%. The oxygen will adjust in the amount because oxygen is highly reactive compared to nitrogen. Nitrogen is non-reactive. Okay, so inert gas. Okay, if we speak about inert gas, those gases are noble gases. Okay, non-reactive, meaning it is already stable by themselves. We don't need any partners for any reaction to proceed. Okay, stable, just like a millionaire, okay, a rich man, a billionaire, a person that's a lot of investments, something like that. So this is stable, the inert gases in the last column of the periodic table. So neon, xenon, krypton, argon, so those are inert gases. That's why argon gases are used in purging vessels and tanks in a confined space because this will never react to other chemical substances. If there's no more reaction to other substances, we are very, very safe. And there's no explosion will be happening because there's no reaction at all. Okay? Highly stable by themselves. Those are inert gases and noble gases. Okay? If the question was in the board examination, which of the following is a noble gas? A. Oxygen. B. Sulfide. C. Neon. D. Like that, your answer will be neon. All gases in the last column, in the periodic table. Neon, neon, krypton, argon, xenon, like that. Okay, put that now in your brain cells. Okay, but the K term there, non-reactive and highly stable. Okay, solo, alone. Okay, no need others to help them. Okay, no need others to, in order for them to be stable, of course. Okay, like that. So that's the purpose there. Okay. So, but in our studies in science, chemistry, physical chemistry, physics, thermodynamics, or some unit processes, right? Okay, we are taught about ideal gases too much. That's why we have a lot of equations, around 12 to 14 equations of ideal gases. Okay, but for non-ideal gases, we have at least 2 or 3 equations. Okay, primarily originated by the van der Waals equation. Okay, like that. Okay, now what are those properties of kinetic molecular theory or theory behind that? We have at least 5. Okay, anybody can answer? This discussed also in chemistry in high school. Okay, and again, it will come back in first year college. Like, and again, it will come back also sometimes in the board examination. Okay, sometimes, not all the times. Okay, like that. There are 5. What are those? Charot. Okay. Okay, the volume of the gas particles are negligible. Okay, are constant, meaning not measurable, meaning dimensionless. So it will matter now for the volume. Okay, you get the point? Meaning to say irrelevant, negligible, constant, something like that. Okay, it will never change that much. For example, the problem I saw, we give only one volume of ammonia throughout the chemical reaction, but that will be enough to proceed the chemical reactions all throughout the process, right? I don't need another volume of the liquid. I don't need another volume of the ammonia. In the chemical reaction, okay, analyze this. I don't need another volume of magnesium hydroxide. Enough for us that we need one volume only of ammonia so that we can solve how many grams of magnesium nitride necessary to react to this kind of chemical reaction. Okay? So this is very clear. Okay, number 2, particles are always moving in a random motion. Or particles of a gas are moving in a constant random motion. Meaning to say, turbulent. Okay, not laminar. So if this is a pie and the gas will flow inside, the ideal gas law believe in erratic movement. Like that, erratic movement, erratic motion, something like it's not straight. Okay, something like that. So gas particles move at a random, constant motion. Okay. 5 ha. If you can write that in your paper, then much better. Number 3. Okay, gas particles collision is elastic, just like a rubber band. Elastic, stretchable, or subject for elongation, something like that. Okay, so elastic meaning the kinetic energy is conserved. Okay, but not the metal. Okay, okay, the total kinetic energy is conserved, meaning there's no loss of kinetic energy. Kinetic energy is always considered throughout the entire process. Okay, in this situation of the gas particles. Okay, collision. Elastic, not inelastic. Okay, kinetic energy is conserved. Okay, means kinetic energy is not zero. Okay, there's always have a value for the mass. If you try to compute the mass, so we compute for the mass a while ago, right? Mass of magnesium nitride. Okay, we'll always compute also if necessary the velocity, how fast the ammonia will escape to the atmosphere, something like that. Okay, that's number 3. Okay, number 4. What else? Particles of gases do not attract or repel. Okay, meaning no need force to be exerted among each other. Why? Why? Remember, gas molecules are very, very far from each other. They have a very wide distance. Okay, no need for them to bump. No need for them to collide. Okay, they can just escape and moving in random motion, something like that. So, do not attract, do not repel, do not exert force each other, and do not react with each other. So in that situation, that's why in ideal gas law, intermolecular forces are not considered. Okay, that's very clear. And number 5, the average kinetic energy of the gas molecules are highly dependent on the temperature. If the kinetic energy will goes high, your temperature also will goes high. For example, if you heat the water, you make coffee, okay, you make coffee and the water will evaporate, liquid molecules will evaporate and it will become a gas, something like that. Okay, the kinetic energy is always increasing also. Okay, if you have a very high temperature, okay, something like that. And the more it is faster to boil if you have too much temperature. Okay? And remember, ideal gas is too much temperature. So the theories really coincide because we said earlier, ideal gas requires higher temperature and lower pressure. But now we heat the water with a higher temperature. Okay, the kinetic energy also increases. Okay, and then that's the time that these molecules are far from each other, will really escape to the atmosphere, and the volume will decrease. Okay, if you increase the kinetic energy, you increase the temperature, automatically your volume will decrease, and also your number of molecules. Okay, it will become lower the volume, something like that. Okay, that's the point. There are 5 theories and concepts of kinetic molecular theory which are applicable in ideal gas, something like that. Okay, now before we will end to this live stream, compressibility factor Z is also one identification to determine if it is an ideal gas or not. The formula of compressibility factor is Z is equals to the pressure times the molar volume over the RT. Okay, like that. Okay, so this is equation. A lot of equations already, right? So we need to stock that in our brain cells, huh? If you're trying to face any science examination, remember, particularly board examination. Okay, especially if you're taking science-related courses that requires PRC regulated examination. Okay, something like that. Okay. So that the problems cannot escape anymore. Okay, like that, right? Okay. Wait, I have to show you the compressibility factor formula. Okay, my gosh, like that. Okay, Z is equals to the pressure times smaller volume. Oh my gosh, over R times T. Okay. Guys, I don't have to derive that because no more time. I have another appointment. Okay. Z is equals to pressure times the molar volume over the universal gas constant R times T. Okay. So we can solve now for the value Z. Okay. Again, if the Z is equal to 1, ideal gas. If the Z is not equal to 1, that is a real gas or a non-ideal gas. And be careful when using equations and formulas. You should identify first what type of gas is that. Okay. So that's the tip and technique for you guys. Okay, thank you so much for watching this live stream. I hope you like this video. This is again a problem from Chemical Engineering Board Examination, November 1998. Okay, thank you so much for watching this live stream. If you like this video, you can have a comment in the comment section down below. And then you can also subscribe to my YT channel. And then you can also click the notification bell for some newest updates of the Engr, Eternal Voice, my CHE Diary. Bye-bye, everybody. God bless.